So today I'm going to talk to you about something called Fido, Ruby, OpenSSL, when payments randomly fail. About me, I'm 36 years old, I have a daughter, 7-year-old, I like Linux, Ruby, everything related to space. I work at a small German company, I have all the gear today, it's called Starfish.team. We are about 50, 60 people working remotely, and we do a bit of consulting, especially on the payments and banking industry. I'm originally from the north of Spain, Bilbao. I lived in Denmark for a while, and now I'm settled here in Valencia in a small town called Rafael Buñol. First, I'm going to talk to you a little bit about what we've been doing in my small team for the last 4 years now. It's called in-car payments, and the idea is that this German brand decided that, hey, our cars are not expensive enough. We need to get more money. So we are going to start charging for amazing stuff. For example, if you buy an EQS, you can get a subscription. So your rear wheels turn 10 degrees extra. So you buy the car, your rear wheels will turn 5 degrees, but if you want another 10 degrees, well, that's a subscription. I think it's several hundred euros per year or something. It's ridiculous. But you can buy it from the car screen. But you can also buy other more useful stuff, maybe like fuel for your car, or charging for your electric car, or maybe parking, or maybe a tolling station. You go and get a ferry and you don't want to, oh, I forgot something. Well, you just do it from your car screen and you maybe skip the queue. Not all of that stuff works now, but it's kind of the future vision that, well, we sell the car and then we'll be like Apple, right? With the App Store. We'll just sell more stuff to our customers. All right, so whenever they are going to buy, they have all these nice screens. So say, cool, let's sell the stuff from these nice screens. We just add a store. But the current implementation, and when we started, what they had, ended up always in QR codes. So you started, you added something to the basket. Oh, yes, let's pay for this map update subscription. And then you had to go to your phone, go to a website, and do the 3DS check where you have to go to your bank and enter some code and receive an SMS. And it takes forever, and well, you cannot really use a phone while driving, so you have to be parked. So it was kind of not very useful. Because in Europe, every credit card payment, and slowly throughout the world, requires something called a strong customer authentication. It's also called the PSD2 regulations for those unlucky enough to have to deal with that. And it requires that every payment, you don't just need the credit card number and expiration date and CVV, you also need that second factor. That usually means, oh, you go to your banking application, you click something, or you receive an SMS, and you confirm it in your banking application, and then you can go through. Ideally, you should use 2 different devices, but a single device is also fine, just 2 factors. The factors are usually something the customer knows, the knowledge, like a PIN or a password, something the customer has, like a phone or a hardware token, like a YubiKey, and something the customer is, so maybe a fingerprint or maybe the face identification, and so on and so on. So then they realized, oh, but the customer has a car, right? You're driving a physical device, a car. And the car also has like stuff like PIN to authenticate and a fingerprint reader. And some models even have a 3D camera to identify people. So you sit on your car and if it looks at your face and then it adjusts your seat. So that kind of identification solutions they have. So we should be able to authenticate users in the car. We have at least 2 factors. The car will be the hardware part, and maybe we ask for a PIN or we do the fingerprint, something like that. And yeah, the text will be small, but no worries, I will just read the important parts for you. So the next step for the project was, okay, we now need to convince banks to allow this. We need to convince banks that whenever you go to a fuel station, you don't have to take out your phone. You can just use your car screen to process the payment, like Apple Pay would do with a phone. How do we do this? And then they started discussing with MasterCard and Visa, the biggest card schemes in Europe, and they said, well, we can use Fido. This is an open protocol. It's secure. It allows hardware authenticators to communicate with the backend and verify that someone is the same person that it was before. The concept works like during a phase called attestation, there's a public-private key generated in your device. The public key goes to the server. During this process, maybe there's an additional authentication or verification of the identity. But then after that, during every login or during every payment, you just need to sign a challenge using the private key stored in your device. And that's the same concept that actually with now Google is selling the Google Passkeys idea. It's just the same technology. You just have a private public key, you get a challenge, you sign it, and then you go along. And it allows to use a hardware authenticator for verifying the identity of a user. It's, of course, combined with another factor, which could be a fingerprint. So you get, oh, you want to confirm this payment? Put your finger here. You want to confirm this payment? Look at the camera for a second. So this is what usually Fido looks like. That's a YubiKey. First, there's the attestation process. The public key gets sent to the guy there would be the server. And there's during every login, there will be a challenge. The challenge is signed, and that's it. And the concept was, well, we'll replace the YubiKey with a card, and we'll have a Ruby server being the middleman, and that's what we are going to build for you. So our job was to build a backend. It's a Rails API-only application running on Kubernetes, nothing too special. It's running a gem called WebAuthn to handle Fido. It's open source, easy to use, nothing fancy. And it just acts as a middleman between Visa, MasterCard, Mercedes APIs, just connecting everyone and allowing cars to talk to it and basically confirm these payments and card activations. It's just relatively a straightforward API. So, but the problem is we finished too early. So it was like 3-4 months since we started, and we said, oh, we have a prototype. It works. We built like a fake website that looks like a car screen, and you can do Fido, and the API works, and we can even do a test payment with Visa. And we went to the other team, different company within Mercedes, and we're like, hey, how is your front end going? Oh, we haven't started. All right, cool. So now what do we do? So there was some budget left, and they said we are very cheap apparently for them. So we said, okay, cool, you just do it. And then we ended up doing this Qt QML interface. So this is the stuff running maybe on a fridge screen. So it's this open source UI library that allows to have like custom UIs. That's what they are currently running in cars. They are not using Android or something fancier. And then it also has a Golang binary as a kind of middleman running in the car in a Docker container. And it also, that Golang part does the Fido client part of the authentication, generating a private key, sending the public key to the server, signing the challenges, and so on and so on. So we ended up doing that. That took much longer. And we actually finished that. And that's how it looks in a car. You have your credit cards, and you can set up the authentication service. And it took 18 months to go live. That was a long time. Half the time probably was spent doing certifications and paperwork, but it worked. Only Visa, only in Germany, only some banks. A lot of disclaimers because it never works. But in a few places, in a few occasions, it works, and it's nice. And over time, it's starting to grow. And as the traffic grew, a mystery appeared. We were live, people were paying for their expensive subscriptions. Sometimes they were starting paying for fuel. Of course, fuel payments are much more recurrent. And then we got this error report. On the 6th of December 2023, a payment had failed on production. Okay, some alarm went out, and then we got called to a meeting. Hey, we have a production error payment. We have never seen this before. What is this, Ignacio? EC point, BN2 point, invalid encoding. Like, looking at us, like me and my colleague were like, have you seen that before? Do you even know what that is? Like, literally no idea. We didn't like. Then that looks like our delegated. That looks like our backend, right? That's our product, right? And then the next scrolled a little, and yes, oh yeah, that's definitely a Ruby trace, right? USR, local bundle, gems, cost. Yeah, that's us. We are the only ones doing Ruby here, so that's definitely our controller crashing with an error we have never seen before on production. Okay, cool. Well, yeah, we'll come back to you. We'll investigate. Highest priority, no worries. Highest priority. We'll give you an update. Yes, sure. So we had to take a look at the offending code, and it's not in our application in the sense that we are just passing a public key, and it works all the time. I mean, it went through queuing. It's been working on product. I don't know why it's failing now. So we open the Ruby cause gem that takes care of handling basically public keys, passing them to OpenSSL and processing them. And here we find this line 72 that's currently doing something with OpenSSL, public key, EC, whatever it is, point, new, and that's crashing. That's just saying that whatever we are passing there, it's crashing. And the previous line is apparently concatenating an X04 and an X and a Y and creating OpenSSL. Oh, we Googled this. This is a big number. So it's creating a big number by concatenating an X and a Y coordinate. This is weird. We had no idea what was going on. Like, we remembered EC, that's probably elliptic curve because our cryptography is elliptic curve cryptography. We remember that that's the protocol that we are using for our Fido, but why is it breaking? Why is it breaking now? No idea. So let's take a very quick overview on what the hell this is elliptic curve cryptography thing. So an elliptic curve looks something like this. The red line has this nice shape. It's a curve, and it's a bit weird, and it's super symmetrical. So there's an axis, and they are always symmetrical on the axis. Okay. So I'm not going to go like an hour talking about the elliptic curve cryptography. It's fascinating, but not the topic of today. Just the important parts. You can use them for public key cryptography. They are very efficient on the size of the public and private keys. The whole planet, interesting, has agreed on a single starting point for all the keys. So imagine like A is always A for everything. It's actually, the point is X is something like 4.84 and Y is 3.61 and a lot of decimals with 76 zeros behind. So those are the numbers that the whole world has agreed. The mathematicians have sat down and said, that's a good number to start with because apparently that gives you a good quality of the encryption keys, and that's the standard, and everyone uses that, and end of story. And then the private key will be a secret integer. So basically you are storing a long number, but you're storing a long number in your computer. And the public key is just another point. So a public key will be just an X, a number, and a Y, a number. So that's everything you need to send. A public key, you send 2 coordinates, you keep a fancy number yourself, and that's all. And you use it for public, private key cryptography. So now that we know what elliptic curve cryptography is, can we understand this thing? So the X04 apparently means it's a marker to say this will be an uncompressed elliptic curve public key. Okay, so it just means nothing. It's just elliptic curve public key. X and Y are the points of the public key. All right, and they are 32-byte values. Okay, so we put them together. Oh, and here is the nice thing. OpenSSL decided some time ago that they wouldn't write proper code and they would use just a hack. So instead of passing X and Y as variables, they are just putting them together, creating something called a big number, and just sending it around different parts of the library because they didn't want to like build a different interface with more parts. They just send them all together, the X and the Y, as a big number. It's never treated as a number. It's always then decomposed into X and Y because it doesn't make sense. It's like if you have coordinates 3 and 5. Oh, we have a number 8. Yes, let's use this. No, it doesn't make any sense. They are always then decomposed. So they cut half of it. So half is X, half is Y, and then they process it. Okay, so horrible hack, but now we know what we're doing. Somehow it's saying that the X and the Y are an impossible point for our elliptic curve. They are invalid. We are passing invalid data to this function. Okay, cool. So now we know that we are passing invalid data, but why? No idea. Then, of course, we do the lazy programmer thing, and we go with like, what if it's a one-time thing, you know? The RAM. It must be the RAM. Bad RAMs is one. I heard once that the cosmic ray can flip a byte in RAM. It must be possible. Like I read a Wikipedia article and they say it happened more than you think. Like, yes, sure, but never seen that before, you know? Okay. We were in that discussion, but well, it happened again, right? We got another error. I think it took like a week or so. Now some people were like actually actively looking for it in the logs, and it happened again. Completely different vehicle, completely different situation. No, it's not another cosmic ray happening. No, something else going on. And then the question was like, well, we have gone through certification, we have a QA team, we have automated tests, everything under the sky for testing. So has it ever happened in our dev or QA environment? And the first response from QA, no, never happened. Never seen this before. It works. So then we decided, like, okay, why don't we test every single public key in our dev server? We're going to test them all. We're going to verify if there we have any public key that also produces this error, because I mean, a public key is what? A piece of string, right? You just pass it to the library, and if it blows up or it works. It's not that hard. It's literally two numbers, an X and a Y. Okay. So, you know, all public keys that each with index. And then we iterate through them, and we have a lot of, okay, we have a web author encoder, so we have to decode the public key, and then we have to decode it, deserialize it, and then we have to, in the end, you get an X and a Y out of whatever you have in your database. And then we put the X04, we put them together, and we basically run the same code with a begin and a rescue. If it rescues, well, it will print invalid public key, blah, blah, blah. And then we threw it. Everything we had ever, because we were not really cleaning the dev QA database. It was just accumulating stuff, so maybe we were lucky. Oh, 9 are broken. Out of 2,200, 9 broken public keys. Is there any pattern? You know, this happened, you know, in a certain month after we deployed something. There must be a pattern, right? Nope. The only pattern we found was that the broken ones are shorter. They are kind of spaced over time. It doesn't have like any. We just see that they are a bit shorter. Instead, these public keys. They're always like serialized into a string. The good ones are 103 characters. The bad ones are 102 characters. So my colleague Sergio, who is very pragmatic, he said, I know, what we'll do is we'll generate a key. If it's 102 characters, we reject it. Then we generate a new one. Problem solved, right? And like, I mean, yes, probably. So we can have, like, you know, like a loop until we get a valid key. But I mean, doesn't seem like a very satisfying solution, right? And right now, one out of 250 users will basically not be able to pay. They have activated their credit card. They think everything is set up, and they will arrive to a filling station, and they will be left there like looking like stupid, trying to like pay, and the thing saying, "Oh, unknown error. Please try again." So then we said, okay, maybe we'll do that. We're not saying we will not do that if we need to, but let's try to find out what's going on. Let's take the time to do. So by this time, I think it's been a few weeks. You know, we are over Christmas probably. Let's try to deal with this properly. And then we open our Golang code, because we had been writing some Golang. Disclaimer, we had no idea how to write Golang code. We just had to, because it runs in the car, it uses little memory, it's a single binary, and it's whatever they wanted to have in the car. Okay, cool. I mean, it has been working fine, but let's open that. So we have this ECDSA.generate key, and that's literally a standard code from the encryption library in Golang. I don't think that broke. If we can't be the only ones finding that the public keys are broken, or in this case, that will generate the private public key combination. I don't think the library is broken. Probably not. Let's keep looking. And then we found this interesting piece of code. Here we have some kind of hash with some hard-coded values. Oh, the X and the Y. The private key.x.bytes, private key.y.bytes. So this is actually the public key, but the naming we had, it was terrible. But this is where we are taking the bytes, and then we are passing it to this seaboard library. We are marshalling it, and that will be our COSE key that gets sent to the server. Oh, so we built our own COSE implementation. So seaboard allows you to basically, instead of passing JSON, you pass JSON in binary format. That's the quick summary of what it does. And COSE is a standard built on top of seaboard to send private keys in or public keys within seaboard. So basically, it allows you to send a request to a server passing a public key within a standardized format. But the thing is, we had built our own. We were not using a library for this. Maybe we messed up. I don't know. We are taking the bytes from an X and Y integer. The bytes are transformed into a byte string. Then we put them into a CBOR, which is like JSON by binary. The result should be a valid cose object, right? But sometimes the result is like one letter too small to sort. What are we doing wrong here? Maybe we messed up the padding. Maybe there's something that, it needs to be always 100 and sometimes it's smaller and you need to put, some empty space in front, something like that. It smelled a little. So we did the thing we should have done a long time ago, and we actually started reading the cose standard and we searched for padding. And quickly we saw, oh, when you use cose with ECDSI, with elliptic curve cryptography, please make sure to always left pad with 0 bits to the correct length. So when you generate a random number, sometimes, and you want, a number between 1 and a million, we will probably have like, 6 digits, probably, right? But it might be smaller. It would be 00001, right? It could be a much smaller number if you are kind of lucky. And this is the kind of thing that happens. You have to put zeros on the left to make it 32 bytes. Well, we were not doing that. When we're missing padding, we're missing 1 byte, and sometimes our public keys were encoded wrong and they were smaller. And okay, we found the bug. Now let's try to fix it. How do we fix this properly? What do we do with every existing customer which has already activated their card and is expecting it to work, and they are frustrated and they are waiting for Mercedes support to call them back and say, yeah, it's working? Do we just delete all of those keys and just ask them to reactivate their cards? Maybe we can fix the public keys. I mean, if it's just zeros missing, right? We can maybe put some zeros on them. So here's our monkey patch. Because Ruby is great. Monkey patch in Ruby is the best thing ever. Just take whatever gem you're using, you can throw it in, for example, I know, a Rails initializer, and just rewrite any function you like. So in this case, we made a test and say, okay, we opened cose gem, the key, and then we redefined the piece of code that was extracting the public key out of whatever we were passing. And for those who cannot read from the back, it just takes, well, if x, I make a copy of x, pad it x, and until the size is 32 bytes, well, I add x00, like an empty byte, in front of it, and save it until we have 32 bytes. And I do the same with y, and that's all. And we test it, and it worked. But of course, it didn't pass code review, because this is the kind of thing that you never have, you should never do, right? Whenever cause changes anything, this is going to blow up. Quite probably that you will forget about this and it will blow up whenever you update your gems, and yeah. It's not great to do it like this. So let's try to do it a bit better. So what we ended up building was a little service that takes a public key and does all the work. It decodes it, decompiles it, deserializes, gets the X, gets the Y, adds the padding, and then saves it again. So we don't have to deal with editing any other gems. We just fix our keys, the ones in our data, we fix them once, and now they are fixed, and we can even validate them. So here's some code that applies the padding to each of the coordinates, the -2, -3, the X and Y. Here the apply padding where we are in the 000, that's the byte, until the size is 32, then all the code for decoding, encoding again. And we even built like a validate function that we used in our test, and we also used to be really sure that this bug never hits it again. Any key running through the system has to go through this validation, which will call OpenSSL directly and check if it's valid or not, and return false if it's not valid, and then we have like a very clear error and not these random messages. So it took us only like 2 months. It's actually exactly 1 year ago when the fix was deployed. I realized this morning, and yeah, it was solved. And the same workaround is now part of the Ruby courses. So actually, we're not the only ones. I was trying like I think it was 4-5 months ago. Say, finally, I'm going to just make a patch somewhere because someone else is going to hit the same blocker. And I mean, the padding, it's very easy that some other library can mess this up. And why don't we just do it on Ruby? Whenever we open that, let's just add the padding if the padding is supposed to be there, right? And someone else did it already. And to finalize, I have some learnings to share with you. Things I think we learned. First, your production logs, they are golden, so don't ignore them. In this case, Mercedes is a big company, so we didn't at the time, we didn't even have access to production logs, to anything. So there's a department looking at the logs, literally. But you know, they don't care. They have like a million applications to look at, and they are going to basically ignore any error and any Ruby trace. They will just don't tell you until a customer complains and someone escalates it. So just make sure you have someone who knows and checks and verifies that if there's any error. Your QA and development logs are important too, because what happened, we are 100% sure someone in testing in QA got this error. Maybe they were just activating a card and not doing a payment, but someone for sure got this error, 100%. But then what did they do? Oh, that's strange. I've never seen that. Let's try again. Let's reproduce it. And then they tried it once. They tried it twice. They tried it 10 times. Oh, it's a fluke. My internet was down. A bird was flying. I don't know, whatever. And then they ignored it. No, just make sure someone takes care of also any kind of a strange error. Handle it. Take a look at it. It might be something. And the third learning is that, well, maybe you're writing code in a language you are not super comfortable with, or a tool that you are not an expert in. And we are definitely not experts in cryptography and in Golang. So why the hell did we write that piece of code that does all that cause encoding? Well, the reason I found out very recently was that the library for Golang doing this kind of encoding did not have a corporate-friendly license. So instead of an MIT license, it was something like Mozilla something that required them to publish all the source code of the resulting application. That sometimes doesn't apply for a web platform, but when you have software delivered in a device, you have to literally publish a disk along. It's a whole mess. It was basically rejected by some department again. So they said, oh, it's fine. We just read the library and you just re-implement it our own, right? How hard it can be. It's just 10 lines of code or something. Easy. Well, be careful. If you don't know what you're doing, just be extra careful. Read maybe the original COSE RFC or just triple check it, because it's a dangerous thing to do. The quick fixes when you have in this kind of cryptography topics can lead to weird stuff. And the last learning is be patient. No piece of software is 100% reliable. You have to accept it. You try your best, right? And this kind of thing, we spent a lot of time trying to make it perfect. We did certifications and manual QA and automated QA, all kinds of stuff we tried. Well, some customer is going to see an error sooner or later. It's a bit outside your control. So I think you have to accept it. It's okay. Just take your time, try to fix it, try to think about it on relative terms, not absolute. Oh, some customers are not able to pay. I can't use it. They are stuck somewhere. Well, someone is going to be stuck. That's okay. But let's try to consider how many are working, how many are stuck, and maybe next month or next year we'll try to be half of them. So let's always try to reduce them and reduce them and reduce them and keep the error rates very low. And live with that, because yeah, nothing is perfect, and definitely not the software we write, even if we use Ruby. Yeah, that was all. Questions?
You said that the private key was sending it to the server?
No, the private key stays in the car. Yeah, it stays always in the authenticator in the car. It's the public part, and the public part has that X and Y coordinates. Yeah, the error we have seen is in the public part. So we are generating that private public pair exactly in the car, and then we are extracting the X and the Y bytes. You extract them, and then you put them into a packet, and that's what you send to the server. Yeah.
So with the solution that you provide when you make the change, you have to deploy in all the cars then?
No, the solution we applied it on the backend because it's much easier for us to deploy to the backend than to the cars. There's also a process. The cars get updated and they download new apps, but it takes forever to certify anything. And in this case, we applied it first. So we applied it first to the backend to make sure that every key would start working and would automatically be cleaned before they are used. And then we also apply the fix to the cars, so in the future it doesn't do that crap. And
when they have already the private key, that private key was changed, so they have to renew that private key?
No, because in the car, the private and the public key, everything was fine. The car had the actual correct data. We hadn't exported in a weird format. It was saved in the authenticator safely. It was all fine. It was just that the server had the corrupted public key, missing literally like 1 byte with zeros. So it was adding the zeros there. And the thing is, like, OpenSSL could have better implementation. It says you take the X, you take the Y. Well, if it's a smaller, well, we assume we're missing a 0, right? But no, they are doing this weird crap of putting L together, like concatenating things, and then it just says, well, you have a point in an inexistent point mathematically. And you're like, what are you talking about? It's super weird. Yeah, something. Yeah.
How many people were you working to detect this bug?
Oh, I think this whole thing was between a couple of colleagues and me that we were working on this. Yeah.
2 weeks.
How much time did it take us? I mean, from the start till the fix was deployed, it was like a 2-month process, but we didn't work on this exclusively. I would say that working on this was probably a couple of people for a couple of weeks to figure it out. Yeah, we did a lot of testing because one of the things we did was like, okay, let's test it out, right? So we made, I don't know, 100,000 public private keys, but we did the whole thing with Ruby. We're generating, or with OpenSSL directly. We're generating the keys, throwing it to OpenSSL. It was perfect, nothing broke. And then we said, okay, we need to do the Golang to Ruby. I tried to connect all the dots. So, okay, but that's annoying. That's running in the car. Oh, we extracted it from Golang. We made a Golang binary that just made these keys with the same format. Then we threw it to Ruby, and immediately, you know, after 200 keys, after 300, it started boom, boom, errors started appearing. Okay, well, it's coming from Golang. And then we continue digging. But yeah, I would say 2 people, a couple of weeks, yeah.
It's hard, I think, to find this.
Yeah. We were like, it was something like someone started work on it for a day or something, and it was like, this is horrible, this is crap, and then we were also waiting because it was like, we don't have access to production data, right, or production logs, so you have to request the access. You get maybe a small part, but you don't have the trace, so you have to wait for someone to give you access, and then so everything is slow. Yeah. Yep.
So, better understand what were you doing on the backend, the Ruby part, with the public key? Because,
So,
I mean, if I imagine a public private connection, usually it's the private part, the one that's
yes.
the public key in order to check if it has access to do what it has to do. So what were you doing in the backend to detect that the public key was not?
So we only detected it not when the public key arrived to the server. That would have been better, actually. We were just storing it in the data and say, well, we have the public key, everything's fine. We're actually detecting it the moment you try to pay for something. There's a process where the backend will generate a challenge. So the merchant, imagine the fueling system, will send a request. Hey, if this user wants to buy 60 euros of fuel at this station, can you please ask him to confirm? That goes to the backend part. The backend part generates a Fido challenge, like a cryptographic question, like a piece of a question that gets sent to the car. Then the user has the screen. Are you sure you want to pay? The user sign, and at that moment, the private key is used to sign that challenge. The signed challenge goes back, and at that point, the public key is used to verify, is the challenge signed by the correct public key? And at that point was the moment when the public key is opened and everything blows up. Yeah. Yep.
The error was detected by luck. Someone is looking at server in that moment when the error occurs, or
Oh, how it was detected? No, unfortunately not. It was detected by someone calling the Mercedes support, the telephone number, and just being very annoyed. I have this new feature, and I have gotten an email, a newsletter from you saying it's super nice and I can do payments, and it doesn't work. And that got escalated somehow to us, and then someone, oh, let's open the logs for that date, for that car, and then they saw it. Oh, there's an error here. Yeah. So it was not very sophisticated or smart at all. We are still trying to get better processes because, of course, there's a department responsible. So there's a department for everything. There's a department responsible for translation. There will be a department responsible for driver distraction, a department responsible for the logs, and a department responsible for the server. So trying to get all of those to work together and actually take care of things like this is, yeah, it takes time.
But this, I'm thinking how this could be avoided, and maybe we can think unit test. But for me, it's impossible to think of a way of, I mean, maybe if I'm a highly specialized mathematician in cryptographic, I can think, no, there is a case where, so how can you defend against this that? I mean, is Mercedes going to implement a new department for highly trained mathematicians?
No, no. I would say that the best would have been to detect it during testing time. It happened. It's not like it happened 9 times in like maybe 18 months, but it still happened. That's 9 times we would have easily have an alert saying, well, there's an error, or maybe there was even an alert, but someone decided to ignore it. But not ignoring those alerts and saying, we have a very strange error, let's just spend some time digging into that, that would have prevented that way before going to production with it.
Something like brute force testing with many instances.
Yeah, no, but actually with just the typical testing flow. So it only happened when you were testing also with the front end, with the not usually have the integration tests of the API only. So we test the API by itself, but then we have some integration tests that also test the in-car application, right? So those run less often, but they are still run. And they open the app, they click here, they click there, they complete a card, then they make a payment, then they check that the payment was successful. Those kind of tests, they are running. And some of those tests were failing. The thing is, when it fails and you don't know why, you don't just repeat it and ignore, right? And especially when it fails, it breaks, and there's someone else, there's an alert saying, hey, something broke in the backend. That was missing. We were not careful enough, or we didn't have the tools set up so we can detect those and address those. Yeah.
But it was also specified in protocol, Marco's protocol, right?
Yeah.
You have to find with zeros.
Yeah. It's definitely specified. So actually, if we have to, one of the things is if you really have to write your own of something that maybe it's already built and someone else has done, don't just do the first thing that kind of seems to work. Maybe spend a day on reading the protocol and thinking a bit harder about the problem. Probably we could have seen that. It's if you have things like I need 32 bytes, I think it could have been prevented by someone spending more time on that. But you know how people tend to be. Oh, this works. I copy paste here. Maybe now ChatGPT, please tell me how this works, and just throw it in. So it can happen. Yeah. No, thanks. Okay, I think it's been a lot of fun. I had never done this particular talk before, and I think the questions were quite interesting, so I don't think everyone was bored. I'm afraid I might have been a bit too fast talking, but that's how I usually talk, so well, I can't avoid that. But I had fun, and I hope that you will enjoy it too when you watch this later. Thank you.